Hi everyone. This laboratory is referred to as pulse transients on a transmission line, which is the type of calculations we have been doing in Chapter 2 of Cinema. It's a fairly long lab associated with multiple measurements, but fortunately the setups are not too complex. So let's take a look at the initial setup. The initial setup is very straightforward. We have the HP8012 pulse generator, and we have our oscilloscope. Now, before we connect the oscilloscope and pulse generator, we need to talk a little bit more about the pulse generator. As you can see from the front of the panel, there are many switches and knobs, and all of them obviously have an effect on the pulse signal. So let's talk about the pulse signal. Previously we did an exercise in PSpice where we talked about the various factors involved in a pulse signal. We have the initial voltage, the rising voltage, the rise time, the fall time, all of that information. With that, I'll leave that for the handout to explain, but you should review that and know the parameters involved in a pulse. On the pulse generator, we will set the generator up using this handout and go step by step. Each one of these numbers refers to a number on the pulse generator or control on the pulse generator. Follow that handout exactly before you move on to the lab and connect the pulse generator to the scope. The connection is as shown, simply from the output of the generator to the input of the scope. Now, before we take a measurement, we need to consider a couple factors. The output of the signal generator is a 50 ohm connection. It's actually not labeled on this unit, but it's generally labeled on most of your pulse and function generators as a 50 ohm input. Here's our new Regal unit. There's an older HP unit. Now, the scope input is, of course, 1 megohm. That's the standard value for the input impedance of a scope. So if we connect a 50 ohm pulse generator to a 1 megohm input, we're going to have a mismatch. Now there's a variety of ways we can deal with this, but on our new scopes, fortunately we have a nice feature. If we press channel 1, you will see that I can set the input impedance. So I'm going to set it to 50 ohms. You might have heard a click there, and you can see that the pulse actually changed shape when I did that. Initially it looked like this. When I select 50 ohms, it looks like this. Now for this initial setup, we're going to connect the pulse generator to the scope on channel 1, and then the scope channel 2, but between them is going to be the 50 ohm cable, the 25-foot cable. Now we are going to initially set channel 1 scope input to 1 megohm and channel 2 to be 50 ohms. By using the connections on the scope. So channel 1 is set at 1 megohm and channel 2 is set at 50 ohms. That will match the transmission line, and this is the view we see. The yellow on top is the input signal, channel 1, and the blue on the bottom is the output signal at channel 2. As we saw previously, that the time delay will be around 37, 38 nanoseconds associated with the time delay of our cable, which is 25 feet or 7.62 meters. This cable is a RG58 type cable, so the velocity of propagation is 2 times 10 to the 8th or 0.66 times the speed of light. Once you have set that up, you can change your setup to one that looks like this, which is where we're going to add a T connector so we can put a 50 ohm load. So I've changed the setup to add the T connector and the 50 ohm loads. This is essentially the same as previously, but now I have changed the input impedance of the scopes to be 1 megohm on each channel for channel 1 and channel 2. So now all the impedance matching is done by the cables that we have attached. This is very similar to this handout where the red termination is the 50 ohms. And we see that the waveform is essentially identical. Now we are going to modify this load to be an open. Now that's easy enough to do. All we have to do is disconnect the red load. Now I've disconnected the red termination, the 50 ohm termination, and you see that the load changes dramatically. I can show this by changing the coupling on the scope. So here's the waveform displayed without the 50 ohm load, but with the channel 2 at 50 ohms. So that puts its own termination in. If I turn off the 50 ohms, make it 1 megohm, you can see a dramatic difference in the waveforms, right? The input signal now, instead of going up just to the rise time of the pulse generator, we actually see it go up farther. This is all because of the reflection. If we zoom in, we can see that the input pulse rises. We see the next step at the output. Because it is an open, it reflects the energy back, and that energy appears at channel 1 at this time. I will change back to 50 ohms so you can see the change in impedance. Here we see the time delay, but we don't see the rising voltage from the second reflection. So this is with the reflected value, and the other is with the 50 ohm match impedance. So record this waveform to an image so you can download it and put it in your report, recording both the time delay and the change in voltages. So now we are going to change the setup a little bit more by adding a T connector with the capability of changing the resistive load. So we go from an open circuit. We now have the inputs impedances at 1 megohm. So now we'll insert the short onto the end of the line, and we see a very small little blips on the short, right? But the pulse goes up and then it stays for a while and goes back down. And that is because the input pulse travels down to the load where it is reflected negatively. That negative pulse comes back and cancels out the input voltage. We'll see that in better effect later in the lab, but that is the effect of a short on a line. The voltage goes to 0. So open and then the short. If you want to, you can experiment with the short itself. You can make a longer wire for a short, and that will change the look of the signal. So now we will change the load from a short to a resistor that is between a short and 50 ohms. So I've mounted a 10 ohm resistor to this BNC and we'll slip it on. Now if you calculate the gamma for 10 ohms, that will be a reflection coefficient of minus 0.6. So this is the waveform we see. the voltage goes down. We see a positive voltage here, but that is smaller than the initial voltage, so the resultant is a negative or a step down voltage. We see that reflected at the input when that pulse travels back to the input. So first pulse goes down, reflected at the load, and comes back. So that's with a minus gamma value of about 0.6. We will change now to a plus gamma value, but not an open. This is a 200 ohm resistor, and that gives us a positive gamma of 0.6. We connect it on, and we see the reflection. The voltage initial pulse goes down. We see the rise in the voltage. It is with a positive gamma value, and then that reflection comes back to the source. Both voltages end up the same at the final value conditions, if you will. But we see the initial pulse travel down and then be reflected back. So we've now looked at a reflection in a match system, a short, an open, a load between a short and a match, and a load greater than a match but less than an open.